Thanks for coming. Sorry that I'm a little bit late. So this tutorial is about experimental machine learning using Holoviz and PyTorch in Jupyter environments. And just briefly about myself, I'm doing my PhD at USC, and I work on extracting semantics from unstructured data like images, text, and try to gain insights. So everyone's here. This is the experimental machine learning with Holoviz, PyTorch in Jupeyterlab or Jupyter Notebook. So today's goal is to make your data exploration and model building process more interactive and exploratory. The main goals will be to use Jupyter environment and this visualization library called Holoviz and its ecosystem, and PyTorch to train our model. And then along the way, we will have to kind of use other libraries like pandas, GeoPandas, and NumPy. So I will be assuming that you're familiar with some kind of machine learning pipelines, as well as some tools like PyTorch and TensorFlow. I won't be able to do all the justice to those amazing libraries, but I'll just kind of walk you through the entire workflow of how I usually would do data exploration and model building, as well as evaluating the trained models. So the specific application is multi-class image segmentation with interactive visualization and experimental model building. So the specific problem we're gonna look at is detecting different types of roads from these satellite images. So the image you're looking at right now is a region in Sudan called Khartoum. It's actually the capital of Sudan. And I was given this data set with a bunch of satellite images, as well as some of the road mask labeled by experts. So we see that there's purple line that indicates motorways, like big highways or any ways that cars can usually drive on. And the yellow lines are residential roads where the it's near the people's houses, and the blue lines are unpaved roads. And so the problem would be, given all this training data that we can use, how can we detect the roads that are not segmented by experts? So is it a motorway, residential way? Is it a paved way? So we would like to be able to build a model that can do this work for us. Another similar data, in the same data set, I also had this Las Vegas, which were quite different from Khartoum in that a lot of these roads are actually highways, and rather the landscape of the picture that we get from the satellite images are quite different. So how can we build a model that generalizes these different satellite images is also another question that we can look at. So I chose this topic of road segmentation because it's very applicable to other similar vision tasks. So here we're seeing that the first image, the left image, is the one of the retinal image in our eyes. So given this image, we would like to just extract out these retinal blood cells. I find it kind of interesting that these are kind of similar to finding roads, right, in the satellite images. And also a little bit different case is to extract different parts of your brain based on this medical image. Sorry. And another a little bit different case is detecting text from historical maps. So the input images are historical maps, and we would like to, it's very hard to hire humans to extract out this text. So we would like to extract out this with some automatic algorithm. So here we have a bunch of image tiles from the historical maps, and some nice people label these text regions. And also we can use it for more real life modern images on the right, where we would like to just extract out these text images. So today's agenda would be to first introduce you to Holoviz, GeoViews, and their ecosystem. And then we would like to start using it on our own data set, and then use Param, which is another library in the Holoviz ecosystem, to build our easily configurable neural network model. And then we're gonna kind of bring back the Holoviz to be able to visualize the training process as well as the trained model's performance on our test images. So why Holoviz? So the general machine learning workflow is you first ask some kind of question, and then we go out and get our data. And then once we have this data, we kind of try to understand what these data are about, and then build a model that solves our problem. And then we would like to communicate the results. So what does our model actually predicting? And at each step of this workflow, we need to be able to visualize what we're doing, both the data and then the model. And Holoviz is, and I usually think a lot of people these days start explorative stage of their model building using Jupyter environment. So Holoviz is a nice way to bring this visualization power inside your Jupyter environment while you're exploring and building your data. So sometimes you have to use, because visualization itself can become an entire work, like a side project to do. It's hard to disentangle your model building and data exploration or visualization. But Holoviz makes it kind of easy to combine those two workflows. So Jupyter and Holoviz and PyTorch, and you can actually extend it to TensorBoard. So it makes this workflow very easy. So for this tutorial, I would like to go through this workflow with you and then see what we can do. So the first question would be, as the images showed, to segment out the roads from satellite images. So it's a supervised machine learning question, meaning we need both the input image data as well as some labels of which pixels in those images are roads or the type of roads. So if you're just concerned about road versus non-road, it would be a binary classification. But we actually want to go one step further and then do multi-class classification. So we would like to distinguish if it's highway, residential, footway, or not a road. So here are some of the data that we're gonna look at. And you can see that sometimes it's actually really difficult because there are the shades from the trees and other buildings, and just the raw pixel value in your image doesn't necessarily tell you whether it's a road or not. So this is one snippet of the visualization that we can make using Holoviz. So we can compare these two examples. The image, and on top of it has the mask. And then on the left, you can actually download external data from OpenStreetMap or other database online by using the georeference in your original image. So here you're looking at an interactive GUI where you can see your data on the left, and depending on the bounding box of your region of your image, we're automatically fetching the data from the OSM and then visualizing it on the right. So we can use this tool to explore our data. And here we're actually seeing the input data from this challenge called SpaceNet, where most of the satellite image and the mask are coming from. And one good thing about it is that you can actually hover over these images and then see the labels interactively, which is I find it almost not possible using like Matplotlib, even though I really think it's a great library. There are some interactive, I think Holoviz adds that interactivity. And we're gonna, so this is kind of in the middle of the training when we use the input data of more common type. We see the mask, the ground truth mask on the left, and then on the right, we see the prediction in the middle of the training. So it's trying to kind of predict that it's a cat and there's the background, but we see that some of these are actually not fully trained. So in the middle of the training, we can actually inspect what the model is learning and how well it's performing. And then at the end, we can give some test data and then interactively, as we vary, it's like a GUI in your Jupyter environment where you can use the drop-down box or slider in your GUI to input your test data and then run your model in the backend automatically and then see the result on top of your test image. So the first step is to introduce Holoviz libraries. So it's a I think I first started to using it this summer for like a large geospatial data visualization. And I found it really useful and also very applicable to machine learning tasks. So, but unfortunately, we'll be touching only the tip of the iceberg. But they have great resources online, like their tutorials, talks in SciPy, and their user guide and examples are really great. So the key principle behind Holoviz is that it's a declarative visualization tool, not imperative, which means you kind of tell what you want, and then it'll give you the visual representation instead of the steps that you have to take. And it's also data-centered, not plot-centered, and we'll see more about what that means. And it's about annotating your data directly with semantics of what your data means. For example, if I just give you a NumPy array, there's no content about this, right? What does this value mean? What does when I see it as a plt.imshow, what am I seeing, right? So, but Holoviz kind of helps you annotate, oh, x-axis means latitude, y-axis means longitude, and the value you're looking at is actually temperature. So it helps you to add those annotations into the data set that's just about the numbers, that's more like a storage. So it's a good way to annotate your data. And it's also a great way to separate your data content from visual representation. And that way you can combine different data elements and then build more complex visual representation. Just briefly about what it means to be data-centered. It means that, so I'll just read verbatim from the comment of one of the core developers. He says, personally, I don't want a grammar of graphics. I want a grammar of data where the data happens to have a graphical representation. I don't want to spend ages piecing together a fancy plot. I want to spend just a little time annotating my data to declare what it means. And then no matter how I slice and dice my data, it'll show up in a meaningful way. That way I can explore it to easily understand it, which is the point of Holoviz. So the core parts that we're gonna explore is its interactivity, and start with the data, not the coding, and avoid entangling your data, code, and visualization. And then we're gonna do all of this in Jupyter environment. So maybe we'll come back to this later. So I think we can now go to the GitHub repo. I don't know if everyone has the access to the repo. So it's github.com/COCOAAA and PyData LA 2019. If I can connect to Wi-Fi, just give me 1 sec. Yeah, COCOAAA. It's also in the schedule, the PyData schedule in my abstract. So it's github.com/COCOAAA /capital P small y capital DADATA /LA -LA 2019. Yeah, sorry. Let me try this. Shall we? Okay. So there are two main building blocks in Holoviz. The first one is container, or the first one is elements, type element, and the other one is type containers, which are the composites of elements. And some of these examples are taken from Holoviz tutorials. So first, elements. The first element we're gonna look at is Holoviz points. So HV means Holoviz. And so here, the way we make these Holoviz objects are you pass in your data to the Holoviz constructors. So here we first define points by a set of points, and then we do Holoviz points, and then we give our data points. Sorry. So we just go through all the imports. Oh, so you can actually open up the binder. So if you go to the README of the repo, there's a small binder button that you can just click, and it'll spawn up the binder environment where you don't have to actually install the libraries yourself. And then you can just follow along the notebooks. It may take some time to start it up. Oh, no. So if you go to the README, if you just click on the repo, there's a README, and then there's a small button that says Launch Binder. And if you click on it, it'll start a new environment. It'll show you that it's building, and after some time, it'll put you in the environment where you can just test or try the notebooks. It'll also download some data. Sorry. So this is the repo, and then here you can click on the Launch Binder button. And if you click on it, it'll build a new environment. So first we need to import all the necessary libraries. So here I'm importing some basic ones, including Holoviz here. So we do import Holoviz as HV, and then some options that we're gonna use for stylizing our visualizations. And then because we're running in notebook, we need the hv.notebook extension. We're gonna use bokeh, but you can also use either Matplotlib or Plotly and other extensions. And in the bottom, we're setting some default visualization options. So for here, I'm just using that for RGB type data, I'm gonna use a certain default settings as well as images, points, and path and tiles. Okay. So finally, elements. So the way we use these constructors are we pass in our data object to our element type, and then we use dimension annotations. So there are two main dimensions, which is called key dimensions, KDIMs, and value dimensions, VDIMs. And so key dimensions are your kind of independent variables, and VDIMs, you can sort of think of it as these dependent variables that you want to specify. So here, back into our points, we can say that the points that we're gonna draw are these, on the x-axis, it's 0.1, 0.2, 100 points, and then for each of these points, we're gonna define a function that computes the sign of that x value, and then give it to hv.points. And here we see that we get this little, a bunch of points here, and we actually are able to hover over these plots and then see the values. And if you do this Holoviz object.dimensions, we actually get the default dimensions. Here, x and y are the default dimensions. Another Holoviz element is Holoviz curves, which represents a set of sample pairs, x, y, that are assumed to have a deterministic relation. It's basically, think of x sample from this one-dimensional space and y as some function of your input x, and then plot it as a curve. So here we give the same points, and then we use curve as the different element type. And in this case, instead of the previous points, we get the curves. So a simple exercise we can do is let's make a curve representing a function f that is the sigmoid of your input x. So sigmoid is one of the activation functions in your network, and it's defined as 1 over 1 plus e to the negative x. And you can use any x as your domain. And let's try this. Zoom. So first, we need to give the range of x values we want to show, and the y values would be this sigmoid x. So in this case, I first define my sigmoid function, 1 over 1 plus numpy dot exp to negative x. And my x's will be just from negative 10 to 10, and I'll sample 100 points. And my y's will be the sigmoid of that function. And if I draw the curve, it shows me this curve of sigmoid from negative 10 to 10. That's your x and your y. And another element is Holoviz scatter, which express a dependent relationship between two variables. So in this case, unlike the previous points, x is understood as independent variable, y as a dependent variable. So even though we see the same plot, they have a different meanings. Maybe this is. So there are two different types of annotation tools, simple annotation tools that you can use, which is the H line, which means horizontal line, and vertical line, V line. So here we see that we define some of these new objects with y value at 0, 1, and 0.5. So these are the horizontal lines at these y points. And I can change the options by using this .opt and then give some styles. And all of these are supporting the Shift tab, so it gives you the keywords that you can use. And in this case, I'm using color and line dash and line width. And by combining with the sigmoid visualization, I now get some more annotations. And by using this overlaying operation, I can keep adding new elements on top of my previous Holoviz objects. So I added a vertical line here. And I can kind of change the other settings like the width and the padding. Padding means the padding of your visual representation. So another quick exercise that we can do is in the data folder, there's a CSV file called ice cream, which shows 1950s ice cream consumption versus temperature, income, and price. There are only 30 points, but I found it quite interesting. So we can first read the CSV using pandas, and then try to explore the data set using some of the tools that we covered. So here's the starting point. So import pandas as PD, and then we read the data using PD read CSV. And then we see that cons means it has 4 columns named cons, income, price, temperature. And cons means consumption, and income and price and temperature. So we can use Holoviz curve or points and then see how these two different variables are related. So here's my version of what I tried. So I passed in the data, which is the pandas object here with 4 columns. And using the key themes, which is adding your annotation, I'm saying when I make this curve using HV curve, I want to use temperature and cons, those 2 columns as my key dimensions to my curve. So it's going to use temp on your x-axis and cons as in your y-axis, and then show the plot. So on your x-axis, you see the temperature. On your y-axis, you see the consumption. And it shows that there's not any pattern into this, it seems. So people like ice cream regardless of temperature. But if you want to actually show that, oh, now I actually want to see the income as well, what we can do is in our opt, we can just pass in the name of your column as your size of your scatter points. And then we see that these are, the sizes are now normalized to your income values. I had to use the normalization because incomes are much bigger than these other values, so they kind of appear all too big if I don't make them in the scale of 0 and 1, in this case, and then times 10. And then the color specifies the black of your scatter points. Moving on to Holoviz image, these are more what you expect as like PLT IM show. So I'm here just showing this image. So I'm just plotting some X and Y grid, and these color values are showing the sign X plus Y. And you can specify different bounds of your image. On the first one, I'm showing -1, -2, 2, 5. On the second one, I'm using just the 0 and 3. What's more interesting to see is our actual data. So in the data samples, there's some sample images that we're gonna use. One of them is just real life image. So we need to, so ski image is just another library that helps us read those images. And regularly you would just call plot IM show, but in our case we can use Holoviz image. And Holoviz image is actually just for 2D data. So I had to just grab one channel, the first channel. And Holoviz RGB is the one that we would actually use to import 3-channel RGB data. And just a simple example with generated synthetic data would be that here I define my domain of X and Y using mesh grid. It just kind of defines your coordinate space, and RGB are the actual values. And by passing in this RGB as a stacked array, it gives us this RGB images. And these are actually like all interactive, so you can move along and then see the values and explore. And if we actually pass in now the actual image, then we see the RGB, the full RGB, instead of just the red image. So I think because of the time, we can sort of move along, skip this exercise. And there are another building block of Holoviz is containers, which combines different elements and then build this more complex Holoviz object. So the first operation that we can use is this star, which is kind of like multiply, but so we multiply 2 Holoviz elements, meaning we put them on top of each other. And layout means you put them on side by side. So we use plus sign for this. And there's another type of container called Holo Maps, which is useful for defining different parameter spaces. What I mean by different parameter spaces is if I have a function that takes in 2 parameters, here sign array takes phase and frequency. So these are 2 different parameters. I want to be able to show multiple images while varying these values. So what I can do is I first define the function that takes in 2 arguments, and then build a Python dictionary that generates all images by giving different values to this frequency and phases. And if I do that and then pass into this HV Holo Maps and specify what are my 2 parameters, in this case, the name of your arguments, phase and frequency, then it actually gives you this kind of slider that that makes your values change. So this phase comes from these values that you pass in as your phase values, and frequency comes from the values that you pass in your dictionary. So we see that these values, as you change these values, these new Holoviz image objects are being shown. So this is nice, but one drawback is that you kind of have to specify and build all these images before you explore. But then if your images are actually too big or your visualization becomes too complex, this is a problem. What we would rather want is just have these Holoviz image or Holoviz objects built when we change the values using the slider. And what enables us to do that is Holoviz dynamic map. And let's move on to Holoviz dynamic map. And you can go to the 01B Holoviz DMAP Gaussians. And we're gonna quickly see how we can use it to build some Gaussian distribution visualization. So this is the notebook, the new different notebook. So in this case, I first need to define what I want to draw. So I'm saying that my x's are these linearly spaced values between -5 and 5, and I want 100 points. And my y's are the Gaussian values, just 0 mean, standard deviation 1. And I'm going to plot the curve and add some annotations as we've seen before. And I'm going to overlay these elements using the star operator. And the result would be this. So that's one element. And just briefly, we can actually extend it to 3 dimension, which is sorry for the size, but I think if you actually use Plotly library here, it gives you the interactivity much better. Maybe I can show you in my. So if you actually install Plotly, I don't think it's installed in the binder at this moment, but if you do like a pip install Plotly in your environment, and then you'll be able to see a 3D plot, and you can actually change the camera angles and then see how it actually works better. So once we define this 3D Gaussian using this draw Gaussian 3D, and we pass into the dynamic map here, then and then specify our key dimensions as before. In this case, those are the arguments that defined here. So mu mean in x dimension, mean in y dimension, sigma in x and y, and then xy is just a cross product. We will not play with it at this moment. And then you see that you have this knobs where you can change these values. Again, if you use Plotly, it should be able to move around these Gaussian distributions and then show the interactivity there. So I think now we can move on to more of the PyTorch part of it. So PyTorch, how's everyone doing? Sorry for the technical glitches. Oh, is this the case for most of the people? Who's able to launch the binder? So are we ready to just move on to PyTorch part of it? Yes? Okay. I'll try to fix everything after tutorial, and you can go back and try those again. So the way PyTorch, the way I think of PyTorch workflow is like this. So we first need to say how we're gonna input our data, and we need to define our loss function, and of course define our model, and then the optimizers will basically have a link to the parameters inside your model. So for example, your model can have some convolution layers, and the convolution layer has weights and biases in PyTorch, and these are usually, and then the parameter type data, and they are tensors, and they are trainable. How many people are familiar with tensor instance of PyTorch? Great. Okay. And parameter is built on top of tensor. It adds the functionality of tracking this auto differentiation, which means when you do computations on your tensor, it keeps tracks of the computations that you're doing on top of it, so that when you do gradient descent, it knows what to do automatically without you specifying what needs to be done to compute the gradients. So once we have this model optimizer, loss function, and data loader, you need to do this mini batch gradient descent. So this is one iteration of mini batch. So data loader gives you X and Y, and then we need to send this data to the correct device, oftentimes GPU or sometimes CPU, and that's what this two operation of the PyTorch tensor is doing. And when we do model and then call this function defined as under call in your model, it will do the forward computation on your input X. And then it'll give you the output prediction of your model. And then we use our loss function that we're going to define to compute some kind of loss between your prediction and target Y. So at this point, your this loss is also a tensor that has been computed using your input and the target Y. And then we need to make sure before we do any backprop that your parameters gradients are 0, because usually, because we don't want to accumulate gradients unless that's the desired behavior. So we call optimizer.zeroGrad, which makes all your parameters attribute called grad, and it sets it to 0. And when you do loss.backwards, it calls the auto differentiation on all the parameters that you're training. And then it puts the gradient of your loss with respect to each parameter into the parameter's grad attribute. And then when you do optimizer step, that's when you actually use the learning rate and some other optimizer specific operations to update your parameter value. So here, P is a parameter of your model, and then it uses the gradient that's been accumulated from your backprop and the learning rate to update its value. So we can go back to the Jupyter notebook. So the first step is to input your data set. And just need to run this for the imports. And here we're importing the PyTorch library. Standard imports like torch, torch.nn, which has an nn function, optimizer optim. And here torch.util.data has the data set and data loader, which we will use to build our own custom data sets and data loaders. And so this is one example of the PyTorch dataset. And here, so dataset needs to have two attributes. The first one is this under length, and another one is this get item. So what it is for is when you do length of an array in Python, like len of your array, that's when this function is called. So it returns the result of this under length function. And this get item is when we do your array and square bracket, like 0, it returns the 0th element in your array. And under the hood, this is the function that's being called. So when you do this square bracket, it actually do array dot under get item and 0. And it does the behavior that you defined in this function. So let's take a quick look at this data set. So I first, at initialization, I give array of images, and I can give the labels of what these image labels are, and some transforms if I want to apply, and I'll talk more about this later. And then store them as my attributes. And in my length, I give the length of all my images, and this is so that when I actually pass my dataset object into data loader, it needs to be able to know what the length of the dataset is. And the get item I define to say if it says give the 0th index, the element in the sample in the 0th index of my dataset, I want to give either both the pair of X image and Y the label, or if at the initialization I said I don't want to get my label by passing label for false, I'll just give the X as the image. So in the get item function, I get basically, if it's a two-dimensional image, I always want to give the three-dimensional image because that's kind of what the PyTorch modules, like convolutional modules, are expecting. And if I define any transforms, I apply it before I return the X image. And that's same for the X as well as for the Y. And once I define this data set, I can actually use it like this. So BS means my batch size for training, and my train DS means my training data set. So here I have a bunch of training images that I loaded before, and Z's means labels. And then once I define this data set, so this comes from the Torch util data, and I pass in my data set as well as the batch size that I want to use for the training data. And I want to say every time I get this data from this data loader, I want my data to be shuffled. And this is important because we want to be able to, we don't always want to have the same order in the data feeding, and it helps with your model generalization by adding some noise into your training. So I have a similar data set that's defined in dataset, and it's called segDS. And it's quite similar to the image dataset, but so you can take a look if you're more interested in it, but I think here we're just start to use it just to move along. So here I have the train IDs, which grabs the IDs of the training data, and images. This train data, their images contains all the input images, and train data, their segmentations contains all the mask images. Is this the problem people are having? So maybe for the interest of time, it may be just better for me to go through the whole workflow, and then I'll fix the data. And you can always ask me during the conference for any questions. So let me go through this workflow. So here, ideally when the data is there, we can, the data set says I imported 1537 images. And when you're training, you can add some data augmentation. So when because your data set is fixed, if you want to add some more variations to your training data, you can either change some colors or the rotations. You can move your image a little bit, or do other type of either cropping, like center crop, or rescaling of your data to add more variations to your data. So that's what these transform objects are doing. And PyTorch Torch Vision supports these transform objects where you can compose multiple transforms. And these are callables, so you can, or class with the -- call object. So once you define it, you can actually build your custom transforms. So that's what this tail pattern is doing. So in the tail pattern, I defined a pattern that adds zeros to, or this whatever value you give as your fill, and pass the data to this pad out size, because the input data are 300 by 500, and or sometimes vary. You want to add this padding so that it becomes a square image. So in this case, I say, oh, both width and height, I want it to be 500. So I define these transforms and give it to the segmentation data, and then what it'll do is it'll apply these transforms before giving your X and Y. So that's what this data set and data loaders are doing. And data loader is quite simple once you have the data sets. So you pass in your data sets and some parameters specific to your data loader. And for the training data, I give batch size of 16 and I want to always shuffle. But for validation, I actually don't want to shuffle. So the default of your data loader is batch size 1 and shuffle to be false. So I don't want to shuffle. And then once I have this data loader, I can now move on to building or choosing my model architecture. So one nice way to visualize your architecture is using Torch summary, which gives you a nicer output of your model architecture. So that's the library I'm using. And Torch Vision has some models that you can use. Some of them are pre-trained. And here in model helpers, I define some functions that helps you with further transfer learning. So freeze all. So transfer learning is when you have a pre-trained model that's, for example, trained on some other image data sets, like public data sets like ImageNet. You want to take the pre-trained model, but make it more specific to the problem you're trying to solve. So in our case, we have different images, like satellite images. So we need to kind of change some of the weights and fine-tune our model. So to do that, we need to sometimes freeze all the parameters. That's what this freeze all is for. Or unfreeze all, or just specify some of the ones that you want to train. And here I define my model as fully convolutional VGG16 based model. And that becomes my model. And just to quickly see what this model is actually about, so using the Torch summary library, if you do summary model and input the size of your ideal input, it actually gives you the output shape of each layer in your model. So we see that our model has, it's based on VGG16, and it has multiple convolutional blocks, including conv ReLU, so that's one block, and conv ReLU, and then we do max pool. So when we do max pool, we downsample by a factor of 2. So in this case, now the output becomes 250 by 250. And we do the same operation, conv max pool, and now the size is another half. And then we do conv, we have 3 convs, and then do downsampling. And then we get another half. And then we do another conv, downsampling. And another downsampling up till here. And then this layer is actually where we use the fully convolutional network. How many people are familiar with fully convolutional network? Wow, great. So fully convolutional network is, so usually before it was proposed, the way it was, this kind of architecture model was designed was we would have this convolutional blocks that extracts features from your input. And then we would have some fully connected layers that changes that flattens your last output of your convolutional blocks. and then makes it 1D vector, and then take that as your kind of extracted feature, and then use multiple layers of fully connected layers, so that at the end, if you have 10 classes, you will end up with a vector of size 10, each saying, oh, the probability of being class 10 is at this vector. But the problem is that because fully connected layer expects a fixed size of input when you design your model, it's you either need to have some layer that changes that output of your vector to the input size of your fully connected layer. But if you take a look at it, if you this fully connected operation, it's actually the same as doing a convolutional operation on your output of your this conv blocks. But the good thing about convolutional operation is that it's you can do it regardless of the input size, right? Because if you have 5 by 5 output, you can still do the same convolution. You can still use the same convolution layer as you would on 10 by 10 because it's a convolutional operation. So that way we're not bound to a specific this input size into this kind of classifier block of your model. And so these are just a different way to see your parameters. And one thing I really wanted to kind of talk about was this learning rate finder method that I find very helpful when I train my model. So learning rate is a very tricky thing to tune, and the main idea comes from this cyclic triangle learning rate scheduling from Leslie Smith's paper. And the main idea is that instead of decaying your learning rate as you train, which is kind of what intuitively what a lot of people had tried in the past, we actually want to increase our learning rate at the beginning of your training. And what it does is that it helps you kind of jump around your weight landscape so that it doesn't stuck in your local minima or wherever is close to your initialization position. So by increasing your learning rate, you're actually escaping this not ideal, not optimal not optimal, but flat regions of your landscape and end up with a better trained model. So in a different notebook, 0-C cyclic learning rate, I try to show what this learning rate finder is about. So there's a link to the 2017 paper. And so the basic idea is that you define this triangle learning rate, which is one of the simpler version, where you say how the slope of your increase in learning rate and decrease in your learning rate as you train. And we have this learning rate range test, where you run this, you change this learning rate in the beginning of a couple epochs that you can specify. Here, the number of iterations you want to test. And it'll plot the loss as you test these different learning rates at different epochs. And when you, going back to the 002A PyTorch dataset, when you run this learning rate range test, it's quite slow because I'm using CPU at this point, but when the training goes, we will end up with this kind of loss graph. So you see that on the x-axis, we're seeing the number of iterations, and on the y, you're seeing the loss at this different learning rates. So we see that the value kind of decrease, interestingly, even though the learning rates are increasing. And at some point, the learning rate becomes too big, so the loss really jumps. So the value we want to ideally set is some value before this huge jump. So in this case, I would choose something around iteration 70. So this is now kind of running the test, and you see that this using the TQDM library, we can actually visualize this progress bar as well. But I think I need to. Let me quickly stop this kernel. So once I have this value, say 70, the learning rate was 0.02, and this is the value that I'm going to use for my first round of training. So, and that's the maximum learning rate. So max LR is found by this learning rate range test, and using triangle or cyclic learning rate policy with the model pre-trained fully convolutional 16, and the loss function of cross entropy. Here, cross entropy because I'm doing a classification and using the batch size of 16. So I set the maximum value, and the minimum learning rate is kind of heuristic at this point, but I'm just going to divide it by 3 and then set it as the starting learning rate. And I'm going to do a 30 cycle, and then it'll actually end up with 60 epochs. And once I do this, it'll start training. Sorry. So ideally, I should be using pre-trained. So once I have this model using the pre-trained, it'll start training and then run the model. Let's see. And the run function will end up with this result, which contains the loss function, loss values, and some other metrics that you want to show, like classification accuracy and class per class accuracies. Sorry for the glitch. And using this Holoviz, again, we can view the curve and see the train and validation accuracy. And what I would actually usually do is do this evaluation on the test images. And so I wish I could have covered more interesting parts, but if you see the 30A full workflow for road detection, it contains this full workflow of what you can do using the data of the roadmap road detection data set. So I'll just quickly go over, just walk through what's in there. So similar to before, we read the data, but in this case using some other geospatial library, and then we see that we see the input data, satellite image, and your mask data. And you can build some simple explorers like image pair explorer, where it has these drop downs where you can quickly change the data to what's in your sample data set, and it'll be shown here. And this part kind of shows you how you can extend it to bring in external data source like OSM and use it for your training if you want to. So you're overlaying the data from OSM on top of your own data set. And moving on to the training part, you can see how you can customize and define new transforms like random crop and normalize. And I'll try to fix this repo so that you can see and go through the rest of the tutorial, maybe after everything's kind of fixed. Yeah, thank you for your time, and sorry for the technical glitches.